Okay.
Sorry, Paola.
No, I mute myself. I was chatting with Simone.
So welcome back to this morning session. Our next speaker is Simone Gottlich from Mannheim. Please.
Okay. Thank you first for this kind invitation for the conference in Rome or online, and thanks to Rinaldo and his crew at this point here. So today I want to talk about non-local conservation laws for material flow problems. And in the next 40 minutes, I will give you an overview about what's going on in this research direction and how this work was originally motivated. So first of all, I want to thank all my collaborators, which you can see here. This is a long list since the project began in 2015. And as you can see, some of the partners are now in industry. Some of them have moved to other universities, but other like Jenny or Paula are here in the audience. Or Axel, also to mention, sorry. Okay, first, let's start with the motivation of material flow problems. So we consider a factory where different machines are connected. So you can see here the production units, and they are connected via these conveyor belts. And if we would zoom in into this belt here, we can see there are some parts or objects lying on the belt, and they are transported with the velocity of the belt, and they interact from time to time with walls or obstacles. So to show you the real experiment, we can have a look at the video here. You see the moving belt. You see these cylindrical type shaped parts. You see they came from left, go to the right, they hit the obstacle, and then are redirected in the sense where the velocity of the belt brings them to. Okay, probably once more. So we see again the bulk of parts entering this area here. They hit the obstacle, so there's a kind of congestion. Some of the parts are only transported with the velocity of the belt, and then they are rerouted behind the obstacle. And we see here that no parts enter this area here behind the obstacle. And the question is now, how do a mathematical model look like for this kind of experiment? Are there different approaches to model the behavior of the parts? How can we do numerical simulations to get the right behavior compared to the real data? And what are optimal control issues? So, and if we would have a look at these two pictures here, we see on the left interacting particles, and later on these interacting particles will be described by systems of ordinary differential equations based on Newton's equations of motion, meaning this is our microscopic modeling approach, so the most accurate dynamics we can observe. And then, like we usually do in a model hierarchy, we are interested, starting from this interacting particle model, to derive some macroscopic PDE model. In our sense, this will lead to a non-local conservation law. And then we have the analog of the interacting particles we see here, given by the part density, and we like to observe or to simulate the density evolution. And the story I'm going to tell you is not that straight as it seems here in the talk. So it's not like, okay, we think about a model on the microscopic level, do the derivation process and end up with a macroscopic equation. It was more like, okay, we had the data from the engineering partners, and we started with a macroscopic model first via some phenomenological approach. So this was a one-to-one relation between the experiment and the equation on the macroscopic level. And in the second step, then we derived, let's say, the interacting particle model behind our macroscopic modeling approach. So please keep that in mind. So let's dive into non-local conservation laws. So as we have seen yesterday, for example, in the talk by Mauro, we can set up a setting of equations like given here. So we could think of systems of conservation laws given by this quantity U, where we observe the non-locality inside this flux function here via this convolution eta and U. So of course, we would also have some initial data and some prescribed domain. And possible fields of applications, again, we remember Mauro's talk yesterday, would be some biological stuff or even sedimentation and related fields. The fields I'm going to mention here are traffic flow and pedestrian dynamics, since both of these fields are directly related to the material flow problem we have in mind. So going back to the interacting particle system. As I told you, this interacting particle dynamics is given by a system of ordinary differential equations of second order. So mainly driven by this part here, where you can see m is the mass of each of our particles. We consider capital N particles in our problem. X is the position and y is the velocity. And here the acceleration is mainly driven by two force terms, which are capital F and capital G. So capital F describes the forces between the particles and are given by a spring damper model of this form here. So we see that the Heaviside function is active whenever two parts are too close together, meaning that they collide. Then these two forces here, Fn and Ft, the tangential force, become active. And if this won't happen, as we have already seen it in the video, there are parts that are only transported with a belt velocity. This bottom friction force term comes into the play, which is given by this kind of regularization here, meaning that we have some constants mu b and gamma b. Also m is again the mass, g the gravitational force, and vt, which is also very important. This is the velocity of the belt. Okay, so these two forces now drive the dynamics of our particle system. So in the first step, on the formal level, okay, so we derive the corresponding mean field equation for n to infinity, meaning that we end up with the equation here, where f is the desired distribution. So short f means here f of x and v. So, and very important to mention is that this s of v, sv, sf here, is our force term, where the two forces are involved from the slide before. So F, the interaction force, and G, the bottom friction force. So in the next step, we aim to derive the hydrodynamic limit equation using a monokinetic closure like it's given here. Then we have to do some calculation and integrations. And we end up here with this system of conservation laws given for the density rho in the first line, and in the second line now for the velocity. And again, we have the forces inside these equations given by this G and F star, where F star is now some special integration of F times the density. So, but this is not the end of the story, since our final goal was to derive some scalar limit equation. We used the ansatz that we said, okay, we consider some quasi-static approach, setting these derivatives here to 0, and consider, let's say, G of rho equals minus F star of rho and U. So, and now we have these two kind of equations where we know what's behind these two formulas here, and we now aim to derive a closed formula for the velocity U. So then some calculations yield that this U is directly given, and we can plug it in here in the first equation for the density, and we end up then with a scalar limit equation given of this form. And we see there are two convective parts. One is driven by the velocity Vt of the belt, and one is given by the interaction of the particles here. And this is very important to know, these two parts. They will shortly appear in the next equation again, which I show you in a minute. And then we have to think about the direct correlation of this guy here, which is nothing else than the transport velocity, but also this guy here, which is more involved, meaning that we have to consider the convolution and interpret this in a right way, saying that, okay, these are the forces that reflects the interaction of the particles. Okay, so actually this kind of model was motivated or is very similar to the crowd dynamic model given by, let's say, the same equation, except this part here, which was introduced by Rinaldo Colombo and his co-workers in 2012. And the key difference, as we will, or as we have already seen, is that now here the velocity of the belt is a key ingredient, and which drives the dynamics a bit. And also the heavy side that is used to switch between the regimes, which say either particles are transported with the velocity of the belt or they collide. Okay, so next, this rho will be our part density in the two-dimensional state space. And again, we dive into this equation here and we observe these two guys, which is this dynamical velocity field and the static velocity field. So the static velocity field can be identified or characterized by the velocity of the belt itself. And the dynamical velocity field, which is given here by the heaviside function of rho minus rho max times the I of rho operator, which is nothing else than a collision operator. And this collision operator I of rho is given minus epsilon times the gradient of the convolution here divided by a normalization. This means, in some sense, this epsilon is a positive factor here in front, which gives you the weight of the interaction. And here, this term gives you, let's say, or it can be interpreted as the force term, as we have seen before, which drives the particles into the direction with a lower density. So what about these velocity fields I've already mentioned? So we distinguish between the static velocity field and the dynamic velocity field. So, and again, the setting we already saw in the video is like we have the conveyor belt, we have the parts, and we have the obstacle here. Meaning that, talking first about the static velocity field, we translate this setting into this mathematical one, saying this we have a region A, which is the particles are transported with the velocity of the belt. We have some region B. This is the region behind the obstacle where parts are not allowed to enter. And we have the region C where the parts are redirected. And we observe some angle theta here, which can be chosen appropriately. So, and for the dynamical velocity field, as I already said, we have the connection between the heaviside function and the collision operator. So, meaning again that this dynamic velocity field comes active when we observe density higher than the maximal density given by the original setting. So, and then the collision operator again tried to push the parts in regions with a lower density. So this is really the same collision operator as already introduced by Rinaldo and his co-workers for the pedestrian movement. And also I like to mention that this eta here is a positive smooth modifier, and again, epsilon, a positive constant. So what we can do in the next step is to discretize the macroscopic approach, saying that we introduce a grid in space and time, and we compute piecewise constant solutions on these intervals here. And we also assume that this H is a smooth approximation of the original Heaviside function, where LF is our Lipschitz constant given by F prime in the L infinity norm. And the collision operator here is computed using a quadrature rule given by this formula here, saying that we aim to compute the derivatives with respect to m equals 1 and 2. Okay, then we can set up two schemes. The first one is a roll scheme, so a nonlinear upwind type scheme combined with dimensional splitting. And a second approach could be to implement a Lax-Friedrich scheme, also with a dimensional splitting, as we see here. And we can also see that these two schemes differ in the choice of the CFL condition, which is in the first case given by these two constants here, and for the Lax-Friedrich schemes given by these constants here, where these alpha and beta are viscosity coefficients also introduced by Rinaldo and his co-workers. And what they both have in common is that they mainly use the Lipschitz constant as a key ingredient, okay? And of course, the L infinity norm of the static velocity field. So we have to say that we have to regularize this static velocity field as well. Okay, what does it mean in terms of numerical simulations about the influence of this Lipschitz function? We will observe in a few minutes. Then we started to think about well-posedness of this model. And then I like to mention that there are still results available in the literature. For example, for the scalar one-dimensional case, the work by Amorim, and for systems in multiple dimensions, the work by Agarwal and co-workers. So, and as I already wanted to point out, we have to state assumptions on the things which have a big impact into the discussion we did, meaning that the static velocity field must be regular in some sense, meaning that here we assume that is a C2 function. H, so the Heaviside function, is a smooth approximation of the original Heaviside function, and the derivative shall be bounded, like here the Lipschitz constant again is F prime in the L infinity norm, and the modifier eta has to be in this space here for some technical reasons. Then we are able to prove the following theorem. So given some initial data and also the assumptions A to C, as we have seen, then there exists a unique weak entropy solution rho to the equations 1 to 4, which was the macroscopic model, so the non-local conservation law, and the following estimates hold. So we are able to prove this L1 bound, or here the L1 equality, the L infinity equality, TV bound, and the L1 bound, where we also have constants C infinity, K1, K2, and CT of T depend on various norms of eta and the static velocity field, and also on the initial data. So what about the proof? So the proof is based on a construction of a converging sequence of approximate solutions. And in the literature, I pointed out, usually Lax-Friedrichs type schemes are used to define this convergence sequence. But here we did the calculation for the row type scheme we have introduced. So, and the main steps are again the positivity, the L1 bound, the L infinity bound, the BV bound, discrete entropy equalities, and the Lipschitz continuous dependence on the initial data to prove the final uniqueness. So having all these bounds at hand, we can use again Helly's theorem and some Lax-Ventroff type arguments to prove the existence of our converging sequence. So what about the validation? So now we have a model and we have the well-posedness of the model and how good is the approximation I proposed. So therefore, I want to present two results. One is related to cylindrical parts and the other one to cubical parts. So let's start with the cylindrical parts. And this is actually the setting we have already seen in the video. So what about Heaviside approximations first? So there are actually two approximations we are using for the Heaviside approximation. So the first one here, which is dotted in the picture, is the arctangus approximation, which is shortly here this ITAN, and the other one is the polynomial approximation you see here. So how do they perform? Of course, again, have in mind that the CFL condition is highly dependent on the influence of the Lipschitz constant, and the Lipschitz constant was defined by the derivative of these two approximations here, meaning that we end up with a better approximation, of course, for the polynomial ansatz. Okay, so the experimental setup consists of 192 parts. This is exactly the same experiment given by the engineers in the beginning. And we use the polynomial Heaviside approximation due to the better influence of the Lipschitz constant in the CFL condition. So what we see here are density plots at the time t equals 1.5. We see here the real data from the experiment. So we see that the parts have already hit the obstacle, they pile up and they are redirected here, which also reflects the right behavior. We have some high density region here in front of the obstacle, and we have lower density regions here where only a few parts can be observed. And now in this third picture, we observe the Lax-Friedrichs scheme, which is more diffusive, and it's hard to observe that this density region here is high due to the diffusion, and we have this high diffusion regime around here, our high density region. Okay, and now this was something related to the I norms, so some observation we did. What about some qualitative results? And therefore, we aim to analyze the outflow. So to measure the outflow, we consider the following setting. We measure the amount of parts that have not yet passed the end of the obstacle, denoted by this expression here. And we introduce some time-dependent mass function u of t that counts the measured parts that are located in the region omega 0. So as you can see here, this is now the mass function counting all the parts, and meaning that this expression here is 1 or 0. So n again is the number of parts, and the sigma 0 is the left-sided region upstream the obstacle. Okay, what does it mean? So we see here time against the percentage of parts in front of the obstacle. In red, we see the experiment. So at the beginning of the experiment, most of the parts are in front of the obstacle, and then the amount decreases. And we see all the approximations we did for the row scheme and the Lax-Friedrich schemes, also comparing the different approaches for the Heaviside function. And we see that in all the cases here, the Rowe approximation fits the real experiment best, since here we see something like a tube around the real data, and we also see that the Lax-Friedrichs type approximation is far away from the real experiment due to the high diffusion of the scheme. So we also did the validation for another kind of parts. So these are the cubical parts. And there was a company here who asked us to do the same experiment with another kind of cargoes, another kind of parts. They were interested in quadratic parts on a conveyor belt, so not the cylindrical parts. So now we consider here this cubic cargo, and we are also interested to answer the question, do we observe a similar behavior as before? Then they redo the experiment. So they have this line here, as you can see, this is the conveyor belt. We have again an obstacle, and here we see this quadratic cargo lying on the belt. And what we did a video. Again, we have the real data. The engineers have their own tool to simulate then a microscopic behavior, and we are only concerned with a macroscopic comparison. So now, this is more involved. So we consider again the outflow. So the mass behind the converter or the diverter, so behind the obstacle here. And we also consider different angles. Okay, so before we were in the setting of the angle here of 45 degrees, but here we are also interested in an angle of 60 degrees. So meaning that parts pile up more. And we also had to scale the macroscopic model with the parameter epsilon, which is now dependent on the angle, as you can see here. This has to be done that we get a better match for the outflow to the experimental data. So if it's hard to read for you, I can show you what we can observe. Again, we have here the real data in black, and we have these two lines in blue and red. In blue, we have the macroscopic model, and in red, we have the microscopic simulation done by the engineers. And okay, these curves, they differ a bit, but they are still very close. And this changes if we would consider an angle of 60 degrees. Again, in black, the experimental data. And you see here, they got stuck somehow at this point. And we see the simulation done by the engineers in red and the macroscopic behavior here. So now it seems that the macroscopic model fails to reflect the right behavior. So let us summarize. So in fact, for an angle of 45 degrees, we observe a good agreement between the experimental data and the simulation results. And we were surprised that the macroscopic model is also suitable for simulation of cubical parts, also assuming that they are homogeneous. And we got that the macroscopic model can be simulated faster than the microscopic model when the number of parts is larger than 500. And again, for a direct comparison, we see here a kind of density or the parts that pile up compared to the part density computed by the macroscopic model. So in both cases, the engineers were very happy with the results, and they confirm that macroscopic simulations are really reasonable when the number of particles is very large. Okay, what can we do next in this kind of setting here, and what we have done so far? Today, I have presented some model for the simulation of material flow. We can show that this model is well posed, and we got convergence of the row scheme towards the right model, and we also validate the model for cylindrical and cubical parts. But there's a large story behind. Of course, in the beginning, I said there are optimal control issues that should be answered. Yes, we did this in this work here, saying that the control we are interested in is the optimal packing. So, or in other words, how should the parts placed on the belt that some cost functional is reached and parts are transported in an optimal way on the belt so that conflicts or collisions are avoided. Or you may also think about some network protection, meaning that in the case here for this 2D conservation law, we are not able to formulate a network in the sense that there are some rigorous conditions given as coupling conditions. That's why we decided to do some projection onto the 1D case and then again work with the usual idea of conservation of mass at nodes. And this is done here. And let me mention that if you would do this projection, this non-local conservation law end up in a local conservation law where the velocity of the belt mainly drives, let's say, the dynamical behavior. And we also did some treatment of boundary interactions since we have this interaction with walls and obstacle. And this is recently investigated in this work here, where we also did another kind of approximation of the or derivation of the macroscopic model, leading to a new kind of model that is a diffusion-based model. So what's going on next? You may ask, what about the parameters you have used in your modeling approach? And this is a valid question, since parameter calibration is a very hot topic here in this material flow setting. So far, we choose the parameters related to examples given in literature or by the engineers, but we could also do some rigorous calibration since we have the original data. And if we would use this ansatz here, some optimal control formalism to calibrate the parameters, we could do the following. So we replace the physical inspired models by neural networks, meaning that we don't assume that there's some interaction model given on the microscopic level. We say, okay, this should be given by the neural network itself. Then we train the network with the real data and compare the resulting forces. And we did this for traffic flow and so in the social force model. So in both cases also related to real data. And we observed in the traffic flow case that this gives a very nice interpretation. But for the social force model, it's not clear if now the social force model or the neural network approach gives you the right dynamics. So there we have a mismatch between the forces that can be seen in the evaluation pictures. So, and the idea is now, since we have also a rigorous analysis of the optimal control problem, at least on the microscopic level so far, that we can apply our ideas to the material flow problem, train the neural network again, and try to get some other interpretation as the model we have already seen today. So I want to stop here and thank you for a kind attention. And I'm very happy to answer your questions.
Questions?
Thank you, Simone, for talk. I have two questions, one theoretical and the other one relevant to modeling. If I understand well, the Heaviside function appears, the discontinuous Heaviside function appears in the model, but then both for numerics and for the theoretical result, you regularize it. Is it right?
Yeah, that's right.
Have you thought of trying to do the theoretical part with the formulation of discontinuous flux conservation law, but not discontinuous in space, discontinuous state variable, there was a formulation of this kind developed by Gottlich-Guerra between Varsap and Prague. So they introduced kind of inner variable which parameterizes the heaviside graph, and then they use, roughly speaking, conservation law with respect to this new variable, and they recover most of the results. The only thing they cannot recover is numerics for explicit scheme, because the safe error condition is empty, so is not possible to satisfy.
Okay, since it's very hard to follow, the sound is rather bad. Probably we can have a Zoom meeting afterwards and discuss more deeply the things you've said, or you can provide the reference you mentioned.
Oh, okay.
I'm sorry.
I try to answer the second question. Have you tried to, for the cubic?
Microphone. Closer, yeah.
Have you tried for the problem with cubes to introduce an additional variable which will be the orientation of the parcel, and try to do the microscopic model by taking into account the orientation, because it looks really different from the cylindrical case?
No, you mean so you discuss now the second problem related to these cubic parts, right?
Yes.
Okay, so for this kind of model, we didn't do anything else than the simulation with the macroscopic model we already have at hand. So there, the formalism is missing. So let's say to set up the right microscopic model, or the derivation of interacting particles. So for this cubic part experiment, we did only the calculations via the macroscopic model, and the engineers did everything for the microscopic approach. There's no analysis, nothing.
Okay, hi Simone and Rinaldo. Thank you for your very nice talk.
Thank
I'd
you.
like to know if you can give us a little more information about how you found the best parameters to fit your experimental data. Do you have also sort of analytical results about this inverse problem?
You mean the last slide related to this calibration here, or you mean?
Well, I would be interested in a general analytical result, of course, but is there any case in which you were successful finding the parameters that make your model best fit your data?
Here, for example, in this case, okay,
Exactly.
yeah. No, for this kind of experiment, for the comparison to the real data, we only did calibration by hand. So there, the rigorous analysis for the parameters is still missing. So this is ongoing work at the moment, okay? So here, what we did, if we go back into the model, given here, of course, we have to choose the modifier, which is some Gaussian kernel here, and we have to play around with the epsilon, which has an impact, and then about the two velocity fields, in the sense that we have to find the right smoothing for the static velocity field, and then started to calibrate everything, since the velocity of the belt was given. So this is a factor which was prescribed by the engineers, okay? So, and then we played around and we observed that not only the epsilon has an impact, it's still for the numerical simulations very necessary to have a good approximation of the Heaviside function. Okay, and again, so we started with the Lax-Friedrichs approximation first and observed, okay, this is so diffusive, we cannot observe anything. And then we started to set up the row scheme, where all the parameters I've mentioned before have now influence on the movement of the parts. But the parameters we choose really by guess. So far there's no analysis. And for the macroscopic model, like here, sorry, here in this setting related to all the forces, we choose the parameters given in the literature. So.
Thank you. We will discuss about that again in the future, I hope. Okay. Thank you. Thank you so much.
More questions? Fine. Okay, so we can thank Simone again for the next.
Thank you.
We start again at 12. 12. last speaker of this morning session, Professor Gottlich-Guerra from the University of Milan.
Okay, first of all, I want to thank the organizer for the opportunity of giving the opportunity to give a real talk after the outbreak of the pandemic. And in this talk, we speak about a result I obtained in collaboration with Wei Shen from Penn State University. So here there is the outline of the talk. First of all, I'm going to introduce the problem I'm interested in. Then I will state the main result we obtained. And then I want to go through the main steps in its proof. So the first step is the description of the Riemann problem and its solutions. The Riemann problem is used as a building block to build vector technical approximations. And the final convergence result of the vector technical approximation is obtained by a compensated compactness argument that I'm going to describe at the end of the talk. So let's begin with the problem I'm interested in. When the slide rise. Okay. And the problem I'm interested in is the following one. So I have a 3x3 system of conservation flow written here, and the width which is endowed with initial data in these functional spaces. So this kind of a system can be used to model one-dimensional polymer clothing in an homogeneous porous medium. And what does this mean? It means that we think of having a polymer, a porous media, which is filled with oil. And we want to displace and collect the oil by pushing it outside of the porous media using water. So here, okay. Here, S is the saturation of the water phase, and consequently, 1 minus S is the saturation of the oil phase. This means that in the initial situation where there is no water, S is equal to 0. And at the end, when the oil is being displaced by the water, S is equal to 1, and only water is present. So the conservation of water is described by the first equation written here, and it was described since the oil conservation of oil is 1 minus S. This describes the conservation of water and the oil. And C here is the concentration of a polymer in water, which is dissolved, maybe.
Come preferisci, se parli forte ogni tanto.
See here is the
Switch off.
okay.
Parla più forte.
Okay. I try to speak louder. So here C is the concentration of a polymer which is dissolved in and transported by water. And this polymer is added water to increase its viscosity and hence its effectiveness in this case oil. And we suppose that this polymer is transported by water and does not diffuse in it, and therefore the conservation of the polymer is described by the second equation here. And K instead is the permeability of the porous media, and since it is a property of the media, we suppose that it is a constant in time, but it may depend even in a discontinuous way on the space variable x. Finally, F here
is a given function, and it depends on both the three unknown, and it is called the fractional flow function. And it is the flow of the first scalar equation, and it appears in the flow of the second one. Okay. Now I want to describe the hypothesis that we make on the fractional flow. So it depends on all the three variables, S, C, and K, but as a function of the water saturation S, we suppose that it always has the famous Buckley-Leverett S shape, which is this one. More precisely, we suppose that it is always an increasing function, so the derivative with respect to S is not negative. And when the saturation is 0, it takes the value 0, and when the saturation is 1, it always takes the value 1. And we suppose that the derivative at 0 and at 1 are both 0. So we have here a horizontal tangent always for any value of C and K. And we suppose that the second derivative with respect to the saturation at 0 is strictly positive, while the second derivative at 1 is always strictly negative. And finally, the last hypothesis is that this function has a unique inflection point. So there exists a unique S star that may depend on C and K, such that the second derivative there is 0. And therefore, before this S star, the fractional flow is a convex function, and after it is a concave one. Okay, these are our hypotheses that we make on the fractional flow. And let's go back to the 3-body system. Here there is the vector of the conserved quantities, and here we have the vector of the respective classes. And it is quite easy to see that there are three characteristic families that we call S waves, C waves, and K waves. And here there is the expression of the corresponding eigenvalues here, and then we have the expression of the corresponding eigenvalues. So if we do some computation on the eigenvalues and the eigenvector, we see that the directional derivative for S waves is given by the second derivative of the fractional flow with respect to saturation. And since this quantity changes sign, this field is neither generally degenerate nor generally nonlinear. But since the corresponding eigenvector here is constant, the integral curves of this characteristic field are straight lines, and therefore Schocker and diffraction curves coincide. And then, if we compute the same expression for the other two fields, we always get 0, so the other two fields are linearly degenerate. Their integral curves are not straight line, but since they are degenerate field, also for this field, the Schocker and diffraction curves coincide. Okay, so what is the main problem in the study of this 3x3 system of observation flow? The main problem is that there are regions in which hypervelocity is completely lost. Indeed, if you look at the first two eigenvalues here, we see that the first one geometrically is the slope of the tangent to the graph of the fractional flow, while the second one is given by the ratio between the fractional flow and the water saturation. Therefore, the first eigenvalue is the slope of the tangent, the graph. The second one is the slope of the segment that connects the point from the graph to the origin. And because of the hypothesis we made of the fractional flow, there is a unique point that we call S tilde that may depend on C and K, in which these two eigenvalues coincide. But also this second component of the eigenvector for the C waves becomes 0, and therefore both the eigenvalue and the eigenvectors coincide in this point. So we have a surface here described by this equation in which hypervelocity is completely lost. And there is another region, the one with S is equal to 0, in which all the three eigenvalues and the three eigenvectors coincide. But this region is easier to take care of. Okay. Now, before going forward, I want to state the main theorem, which says that given these three by three system of conservation law with the hypothesis I made of the functional flow F, and given initial data in these functional spaces, then this Cauchy problem always admits at least a weak solution. So more precisely, there exist three functions S, C, and K in these functional spaces, such that for A test function P, the usual integral equality that defines a weak solution. This is the main result we obtain. That is the existence of a weak solution in the presence of region without hyperbolicity. Okay, now I want to give an outline of the proof. So here I'm going to describe the main steps in the proof. So the main problem here is that the loss of hyperbolicity means that we cannot rely on the standard compactness argument that we are used to in the study of systems, one-dimensional system of point observation. So what we want to do is that first we do a careful analysis of the Riemann problems in the presence of region without hyperbolicity. And the presence of these regions, in addition to the problem of the lack of standard PV compactness estimate, introduce another problem that is that we have some Riemann problem that have a multiple solution. Therefore, first of all, we need to choose among the solution of the Riemann problem the one that eventually will allow us at the end to prove the final convergence. And then we use this solution to the Riemann problem to construct a approximate solution using the contracting algorithm. And finally, since we do not have a BB estimate, we prove convergence by compensated compactness. Okay, let's begin with the first step. So we want to study first the first type of the loss of hyperbolicity. So the first type of region I described before. To this end, we suppose that the permeability is constant not only in time but also in space, and therefore our 3x3 system reduces to this simpler 2x2 system without the variable k in it. I want to say that we are interested in solving this system in Eulerian coordinates because we want to include the case where saturation S is 0 because it is the initial condition where only oil is present and then not. But if you write it in Lagrangian coordinate, we can see that it simplifies because it becomes a triangular system. Here y is the Lagrangian coordinate, and the polymer concentration becomes constant in time in this coordinate. Therefore, what we plan to do is, okay, before stating our plan, we want to say that it is well known that these two systems here have the same entropy solutions as long as the water saturation is expanded away from 0. And this was proved by demonstrated by Wagner. So what we try to do is the following. We study first the Riemann problem in the simpler Lagrangian coordinate. Yeah, where the value S is equal to 0 must be excluded. And then we try to write the solution back in Eulerian coordinate because we do not want to exclude this. Okay, to do this, to study the Riemann problem in Lagrangian coordinate, we need to introduce this function that we call small g, which is given by the ratio between the fractional flow and the water saturation S. Here there is the graph of the fractional flow with its S shape. And here we have the graph of this new defined function G. Both plotted against the water saturation S. And I now want to observe that the point in which hyperplicity is lost, which is Sept, is exactly the point in which this newly defined function contains its maximum. Another thing I want to observe is the following: that if we look at the system written in Lagrangian coordinate, the flux of the first equation here is exactly minus this function, newly defined function. And so we write here to the right. Yes, okay. Now we write the graph of minus g, which is exactly the flux in Lagrangian coordinate minus g, but we plot it against the real conserved quantity in a Lagrangian coordinate, which is 1 over s. Okay. And we observe that the monotonicity properties of this function g plotted against the separation s are exactly the same as the monotonicity properties of minus g plotted against 1 over s. Indeed, there is a correspondence between the region in which both the function increases and between the regions in which both the function here and here decreases. So we keep this observation in mind and proceed to the solution of the Riemann problem in Lagrangian coordinate first. So in Lagrangian coordinate, the polymer concentration C is constant in time, and therefore C waves in Lagrangian coordinate Y travel with 0 speed. So to solve the Riemann problem, we fix a left state here and the right state here, and we know that for every time the right of the origin, the value of C is always C plus here, and while the left, the value of C is always minus. And to solve the Riemann problem, what we need to do is to find two states, S minus and S plus, here, okay, in such a way that, first of all, the left state SL must be connected to S minus by waves having negative speed for this scalar conservation law, where the conserved quantity is 1 over S and the flux minus G. Then, because of ranking-Monod and these waves travel with 0 speed, the function g must obtain the same value at both sides of the wave here. And finally, we need that this S plus must be connected to the right state SR by waves having positive speed for this scalar conservation law, where the conserved quantity is 1 over S and the scalar class is minus G computed at C plus. Here, G was computed at C minus. Okay, so this is what we do. And then we return the observation we made in the slide before. And we observe that as long as we are concerned in finding only these two states, S minus and S plus, we can, instead of solving the original Lagrangian, the first conservation law in the Lagrangian coordinate, we can solve this auxiliary problem here, this one to the left and this one to the right, okay, where the conserved quantity is the water saturation and the flux is G and not minus G. Okay. So we can use this auxiliary problem as long as we are concerned only in finding S minus and S plus. And the point in this is that these two equations are meaningful even if the saturation takes the values. So how do we find these two states, S minus and S plus? We use an old technique that I think it dates back to Gibbs Harris group in 1991. And is the following. So we consider the flux to the left. So it is G computed at C minus. This is its graph. Then we consider the left state for the saturation L. And then we define a new function that we call capital G L, this one, which is defined as the minimum of the value of G to the right of SL and the maximum of the value of G to the left. And this function capital G is decreasing, not increasing, and has the property that whenever its graph touches the graph of small g, is all these states, okay, on the horizontal axis are states that can be connected to SL by ways having negative spin. And then in a symmetric way, we consider the flux to the right of the C wave, which is G of the C plus. We fix the right state for the water saturation. And then in a symmetric way, we define the capital G R, this one, which is defined as the maximum value to the right of S R and the minimum to the left. This is an increasing function. And as the property that whenever it touches the graph of G here, all these states can be connected to SR by ways having only positive state. And then since now we have a decreasing function and a decreasing in another, one function is decreasing, the other one is increasing, there is a unique level at which they intersect. And we call this level gamma, which is the transition level. This is defined in a unique way. And then we take this gamma and define the counter image of this value gamma using first, when we appears, using first capital G L, take the counter image, since it is a decreasing function, the counter image is a general interval. And then we take the projection of SL onto this interval. And this is defined in a unique way, this state S minus, which is the state that we wanted to find. And then we do the same way, the same thing. We do the same thing with the capital G R. We first take the counter image. This is an interval, then we take a projection and define it. So this algorithm defines in a unique way these two states we wanted to find. Okay. There are other weak solutions, the same procedure, the same Riemann problem, but these are the solutions we take because they will allow us to get the final existence results. And why is this? Because if we choose exactly S minus and S plus defined this unique way, then the solution we obtain is the following admissibility condition. Slide right. The admissibility condition is the following. Clearly, the value of G at both sides of the wave is the same, and it coincides with the transition level gamma. But whenever S minus is lesser than S plus, it happens that S minus is less than S plus, then there exists a state in between them that I call S star, such that before S star, between S minus and S star, the left fluxes, the graph of the left fluxes, the left flux is above the transition level. And then from S star and S plus, it is the graph to the right, G component S plus, which is above the transition. This is an admissibility condition satisfied by the Riemann problem we choose with the algorithm I've shown before. And then there is the symmetric condition if S plus is lesser than S minus, then the graph that is below the transition level. Okay. So we are in a position to write the solution to the Riemann problem, to write it back in an Eulerian coordinate. So in Eulerian coordinate, we have the left and the right state as before, but here we have the Eulerian coordinate, not the one. And it turns out that the gamma, the transition level gamma we found before, is exactly the Rankine-Ogognot speed of the C wave in the Eulerian coordinate. Okay. So this gamma is exactly the speed, the right speed of the C wave in Eulerian. And then, because of the correspondence between Lagrange and the Eulerian description, we have that the left state SL can be connected to S minus by wave having positive speed, but the speed is less than gamma. Okay, and this wave have a speed between 0 and gamma for this conservation law here, which is the original conservation law in the 2x2 system, where the fractional flow is computed as C minus. And then the trick is to choose these waves as entropic waves for this scalar conservation. Okay. Not for the auxiliary conservation flow in the G in the flux. So these waves are exactly an entropy solution for this conservation law here, scalar conservation. And then clearly, similar way, S plus can be connected to SR with waves having speed greater than gamma for this conservation law here, where the fractional flow is computed as C plus. And we choose this wave. We choose waves that are entropic for this non-convex. These are two non-convex scalar conservation law. And we choose the entropic solution for non-convex scalar conservation. Okay, so this completed the description of the solution to the Riemann problem for the 2x2 system where the permeability K is constant. And then, if the permeability K is not constant, then we have three states to the left and SL C minus K minus, and three states to the right, SR C plus K plus, and we need to connect them by a solution to the Riemann. But now we observe that in the Eulerian coordinate, it is the variable k that is constant in time. Therefore, in Eulerian coordinate, k waves travel with 0 speed. So k to the left is constant equal to k minus, the right is constant equal to k plus. So we know the location of the k wave for times. And then what we need to do is just find. Since it travels with 0 speed in Eulerian coordinate, Rankine-Gognon says that the fluxes, the original fractional flow, must be equal at the sides of the K wave. Yeah. So what we need to do is just find a state Sn in such a way that two fluxes have the same value. Okay. To the left, with here K minus, to the right, K plus. But this condition defined in a unique way is Sn because the fractional flow is a function. Okay. So f computed at SL C minus K minus takes this value. And then if instead of K minus I put the K plus, we have a different fractional flow, but it is always increasing. So this Sn is determined in a unique way. So we have the uniqueness of the solution, and for this case, we do not need any state condition. And once we have this state for the order separation Sn, then in all this order plane, K plus is constant, and then we can apply the Riemann problem I described before for the 2x2 system. And this completes, this is the complete solution to the Riemann problem for the complete 2x2 system conservation. So before going forward, I summarize the property of the waves we have in the solution of the Riemann problem. So we have k waves, where k has jumps. They travel with 0 speed in their coordinate. And then across k waves, both the flux f and the variable c are constant. Okay. What changes across the k wave is the variable s to the separation, the variable k. But this change must satisfy the quality of the flux. And this determines in a unique way the value at the size of the wave. Then we have c waves. They travel with the negative speed, which is equal to the function we used before, g, which is given by f over s. And across a c wave, we have that the g is constant, because it is the speed of the wave, and it takes the same value to both sides of the wave. And also the variable k is constant across the c wave. And the jump in C, in S and C satisfy the quality of the function g. But this is not enough to give uniqueness, and therefore we know to construct the sea waves in the way I've shown before, we know that across sea wave, the visibility condition I've shown is satisfied. And finally, we have a S wave that travel with a positive speed. And across them, both C and K are constant. And the shock satisfies the usual Archimedean condition, because here C and K are constant. And so an S wave is a wave for a scalar concentration flow. And they satisfy the usual visibility condition for non-convex scalar concentrations. Okay. So this is a summary of all the waves and the properties we have in the solution of the Riemann problem. And now we are in a position to use this solution as a building block to construct wave solutions. So first of all, we fix initial data, the function spaces we'll see the main result. And then we fix an approximation parameter, psi of vector 0, and we define piecewise constant approximation data that we call as epsilon, epsilon. And this is constant approximation data approximate the initial data in a uniform way concerning K bar and C bar, and only the one block topology concerning the separation. Once we have a piecewise constant approximate initial data, we need a grid, a suitable dense grid of value that the function G can attain. And clearly, this grid must contain all the initial value of the function G computed at the approximate piecewise constant approximation data. And once we define a suitable dense grid of value the function G can attain, then for any fixed C and K, we take the counter image using the function G of this grid, and we get a CK dependent grid for the water saturation test. And what is used for this new grid of the water saturation? This grid is used to define the piecewise the linear interpolation. We take the linear interpolation of the fractional flow, and we call it epsilon CK according to this CK dependent grid. So what we do, the picture of what we do is the following. So we fix a value of C and a value of K, and we plot the graph of G against S, which is this one. Then we have a grid for the value that the function G can attain, okay, in the wave-tracking approximations. And then we take the counter image of this function G, which are this one. And we have a grid that depends on C and K for the water saturation. And using this grid, take the linear interpolation of the fractional flow here. Okay. So it's a linear interpolation that clearly depends on C and K. So if the original grid was sufficiently dense, depending on epsilon, then both the linear interpolation here and its derivative approximate uniformly both the fractional flow and its derivative. Okay, now let's describe the wave-tracking approximation. So first of all, we know from the beginning the location of K waves because they travel with zero speed, and we know the value of the permeability K at all times. So here it is constantly equal to K0 epsilon, epsilon, so on. And then we consider the piecewise constant initial data for the polymer concentration. The green dots here are the discontinuity, the point in which discontinuity are, and here are the constant value for the piecewise constant initial polymer concentration. And then we consider the initial piecewise constant approximation, the initial data for the water saturation. And here the red dots are the location of the jumps of the initial data. And then we do this sort of observation. So first we start from the leftmost region here, where we define the grid for the value that G can obtain. So we have seen the slide before. And then we do the following observation. Since C waves are linearly degenerate, we cannot have interaction between them. And this allows us to define regions that I call omega 0 in the T-explain region that I call omega 0, omega 0, and 0. In this region, both C and K are constant. For instance, in this region here, C is constant equal to C1 epsilon, and K is constant equal to K0 epsilon, and so on. So these are regions in which C and K are constant. And therefore, in this region, we can define the linear interpolation of the fractional flow using the procedure we've seen before, where the grid for the function G is kept fixed. Okay. And then we proceed to the solution to the Riemann problem, as we've seen the slides before, at a discontinuity point, and we solve the Riemann problem in an exact way. So we solve it in an exact way, but using this linear interpolation of the fraction. And so we get the wavefront tracking pattern here. And since there are no waves with negative speed, here there are no waves reflected back. So we can complete the wavefront tracking pattern here in this left and rightmost region. Okay. And then whenever a wave touches the first K wave, we can solve the three-way Riemann problem. And we can go to the next region. And I want to observe that as long as there are interactions between S wave and S and C wave, this grid is invariant. This grid of the value of G is invariant. But whenever there is interaction with the K wave, this grid is no more invariant. And therefore, in this new region, we may need to add some value for the grid that the function G can obtain. But we add this value, and then we can build wave tracking pattern in the second region, and we go from the right to the left, and we can have a wave tracking constant solution defined on the second. And what we do with this wave tracking approximation, the main point here is that we have an exact solution of an approximate equation. So we can define a flux that we call capital F epsilon, which is given by the linear interpolation in any region in which C and K are constant. So this flux, capital F epsilon, depends on T and X because from this variable here, C and K, that are constantly in this region omega Ji. So if we define this flux, global flux, capital F epsilon, then it turns out that our solution, our wavefront tracking approximate solution, are indeed exact solution to this 3x3 system conservation that approximate our original 3x system we want to solve. And moreover, this capital F epsilon approximated the fractional flow computed at C epsilon and K epsilon in a uniform way. So what we do from this, so we recall that in our wave tracking pattern, we know that S waves and C waves satisfy the discriminant condition. Any S and C waves satisfy the discriminant condition before, because we solved the Riemann problem in an exact way. And moreover, as epsilon tends to 0, what we already know is that since K is constant in time, the wavefront tracking approximation K converges in a uniform way with the indicator, which is the initial data for K, because of this constant in time. This is trivial. But since there are no interaction between C wave, the total variation of C does not change in time. And therefore, for C, we indeed have the uniform estimate. And therefore, by Kelly's theorem, we know that there is a subsequence that converges strongly to a limit that we call C theta. What we do not have is a uniform estimate on the total variation of the variable S on our Gottlich-Guerra solution. So we do not have really an estimate on S. This is the reason why we need to seek help on the theory of the setting. So what we already know is that we are able to construct waveform tracking approximations that are indeed exact solution to this 3x3 approximate system. So to use compensating compactness, we introduce an entropy that we call theta, a smooth function, and then we define entropy flux. This entropy flux is defined thinking of the first equation here as a single scalar conservation law. So this is the corresponding flux. We view the first equation here in the system as a single scalar conservation law. It is adapted to this conservation law here. And then we want to estimate the entropy production on our waveform tracking approximation. So to estimate the entropy production, we need to introduce a test function of P, non-negative, and then we want to compute this duality product. And clearly, the entropy production is concentrated on the discontinuity of the waveform tracking approximation, and therefore is given by the sum of all the entropy production of the here, where the sum is on all the waves we have in the waveform approximation. So what we do now is to estimate this quantity on the three types of waves we have. So now we take a strictly convex theta and the non-negative test function. And first, we estimate the entropy production on S waves. This is the main point. The main point is that our S waves are exact entropic solution for the first scalar conservation law. And therefore, the total entropy production here is non-positive. And in this estimate, the total variation of S wave does not appear. And this is good because we are not able to control the total variation for S waves. So this is one of the main. Use exact solution for the first scalar, exact entropic solution for the first scalar solution. And then we compute the total entropy production on C waves. Okay. And we obtain that the total entropy production is bounded by the total variation of C bar, which is bounded by hypothesis. And to obtain this estimate, we really need the split coefficient of C waves we have seen before. Okay. And then we compute the total entropy production K waves here. And this is the easiest estimate because we do not need any admissibility conditions since there is uniqueness in the solution where we solve for K waves. And we get that the total entropy production is bounded by total variation K bar, which is bounded by hypothesis. Okay. So all this estimated together allows us to get this final bound of the total entropy production. And using a standard technique in compensated compactness theory, this estimate gives the following result that there is for any smooth function theta, there is a contact set that does not depend on epsilon in X-1 block, such that this measure belongs to this contact set. And this estimate is then used to apply the Gottlich-Guerra lemma. The application of the Gottlich-Guerra lemma here is not standard because we have a flux that depend on T and X in a non-smooth way, so it is not standard application of the Gottlich-Guerra lemma, but I have no time to show it, so I jump to the last slide, which is this one. So through an application, a non-standard application of the Gottlich-Guerra lemma, from this estimate here, we are able to obtain that up to subsequences as epsilon converges to a limit as tilde in a strong way, and therefore that together with C tilde, we've seen before, and K bar is a big solution to the original three-way system of conservation. So here we have the two papers on which this talk is based on. Here in the first one, the solution to the three-way, the Riemann problem for the three-way system solved. And here the second one, the wave contracting algorithm, and the final simple compartment argument and carried out. So thank you very much.
Questions? Online? I think we can